Okay, hey, and welcome to Bio 202 for our brand new week, Monday, March the 30th, 2020. And I don't know how far we are into COVID-19 anymore. It'll be fun to look back on this and go, huh, we survived. But anyway, okay, so I'm glad that you found where I'm at, and we shouldn't have any problems with recordings or anything like that. And remember that tomorrow at 9 a.m. we will have our lab class. So you have nothing in your yellow pack or in your purple packet, obviously. Let me get back so I'm not in the, oh well. I'm in Canada now, in the Aurora Borealis, so I'd share that with you. So I will be uploading a packet for lab for this week. So find that sometime today and then download that so that you can bring it to lab tomorrow. Okay, so we are just gonna go ahead and go into our PowerPoint. So we're in our digestive system lecture notes, and as soon as that wants to cooperate. All right, here we go. So we went through the processes of digestion last week, and I just wanted to reiterate this little diagram showing the two different processes. So peristalsis, you're all familiar with. So remember that this bottom one is segmentation, and this is what's going to happen in the small intestine so that we can mix the digestive enzymes with the food that's coming from the stomach, and then we get good mixing of the food so that we can optimize the amount of interaction that those hydrolytic enzymes are going to have with the food that we're digesting. Okay, remember that we have 4 layers of the alimentary canal wall or digestive tract wall. So the innermost layer is the mucosa, simple columnar epithelium. We'll take a look at the picture again in just a minute. Submucosa, muscularis, and serosa. Remember that there are 2 layers to the muscularis. And then in the submucosa, we're going to have one of those enteric nerve plexuses, and then in the muscularis as well. So we'll take a look at that. Okay. So so here is the innermost layer. This section right here is the mucosa. We're going to look at some modifications to the mucosa today that increase surface area for absorption, and primarily that. Some digestion, but primarily absorption. Here's that simple columnar epithelium that we see, and then we have some other glands, and then we have the MALT, so the mucosa associated lymphoid tissue, like the Peyer's patches, that are going to help defend against anything that we might ingest. Okay, so mucosa, submucosa, this is where we're going to have one of those enteric nerve plexuses. Enteric means intestine. So the submucosa will help with this muscularis internum right here. That's gonna contract, or actually muscularis mucosae, that will help move things along. But this is where we're going to have the blood vessels and the lymphatics that are going to go into the mucosa ultimately in the submucosa. But remember, this is part of our gut brain here in the submucosa nerve plexus, and then we have the muscularis. So the longitudinal layer is the outermost layer, and the circular layer is the innermost layer, and then it too will have a nerve plexus. So the myenteric nerve plexus is the one that controls this smooth muscle contraction here in the muscularis, and then the outermost layer is the serosa. Just this peeled back portion would be the visceral peritoneum. All right, now we're going to go into the stomach. We're going to have a little bit of modification in the stomach over what we find everywhere else in the digestive tract. We still have a serosa, that visceral peritoneum. It's still going to be all the same. But in the muscularis layer, we're going to have 3 layers of smooth muscle. We have the circular and longitudinal that we have in the same as we have in the rest of the alimentary canal, but we have an oblique layer, and I will get to a picture of that in just a minute. And the oblique layer helps to just churn the food around so that's not being moved out of the out of the stomach, but we want to mix it around with the digestive enzymes that are going to be present in the stomach. And also, like it says, for some mechanical digestion. Then the submucosa is going to be the same. And the mucosa, okay, still simple columnar epithelial cells, lots of goblet cells. We need to secrete that alkaline mucus because remember, the environment of the stomach is going to be very, very acidic and would eat away at the stomach wall if it were not for that mucus, that alkaline mucus, neutralizing the acid. But here is the other thing that's important to know about the stomach is that in that mucosa, we're going to have a bunch of gastric pits, which are going to lead to gastric glands that produce gastric juice. We'll go over that in just a second. Let me just show you. So if we take a look at, this is not the same diagram here, but it's this idea. So we're going to have these ducts that are going to come up into the mucosa that we're going to find within our stomach. Because the picture doesn't show it quite as good as that I'm going to show you in a minute. So if we take a look at this, we can see the 3 layers of the stomach wall, the muscular stomach wall. So here's the longitudinal layer, here's the circular layer, and then the innermost one is oblique. So it's going to run at an angle, and that's where you get that gurgly stomach churning sound from. We've got the rugae that are in there that, you know, allow your stomach to expand. And then we have the pyloric sphincter right here, and then on into the duodenum. This just shows with the pyloric sphincter closed, that stuff just kind of smooshes around in there. But if we have enough pressure, we'll get some material moving through, but some kickback stuff. I don't even know why that's in there, but anyway. Okay, so we want to take a look at what comprises a gastric gland. So these are the 4 cell types that we find within the gastric gland. So I'm going to go ahead and go to the diagram of that, and then we'll come back and look at the definitions of those. Okay, so pitted all throughout, all around here in the stomach, in the mucosa. So remember, this is the innermost layer, and then here's the submucosa right here, and then there's the 3 layers of the muscle, and then the serosa. So this is a good thick mucosa right here in that muscular layer there, and then the submucosa. So those glands extend quite deep into the mucosa, but they need to, because we need to have lots of cells. So these are just going to be regular surface epithelium right here, and these tan colored cells, just regular simple columnar epithelial cells. Then these red cells are going to be mucous neck cells that are going to produce mucus as well within the gastric gland. So all of these, just because they're in the gland itself, I guess we give them a different name. But anyway, so they'll produce more mucus. But then there are 3 really important cells we'll take a look at in the lower portion of the gastric gland that are right here. So these little blue ones that look like little circles or little kind of Pac-Man dudes or whatever. Oh my goodness, you guys, these are my favorite cells. Oh shoot, I'll find it for next time. Because I have a little thingy I want to show you about how they work. Because these are guys that produce hydrochloric acid, and it's really fascinating. It's really a great diagram. I haven't. Of course, it's on my desk where I can't find crap, but anyway, I'll find it for next time. Put it in my PowerPoint. So the parietal cell, I don't know how you want to remember that. It's on the edge. I don't know. They're all on the edge. So anyway, this parietal cell is going to produce hydrochloric acid. So remember that. It's also going to produce intrinsic factor, which we'll discuss in just a minute. But the parietal cells then will produce the hydrochloric acid necessary to provide the proper pH for the conversion of pepsinogen to pepsin. So remember in lab, we talked about how pepsin is the enzyme that's produced in the stomach that's going to digest proteins, but it's going to be secreted in an inactive form as pepsinogen. So that pepsinogen has to be converted to pepsin, and it'll only do that in the presence of hydrochloric acid. So So the parietal cells make hydrochloric acid. They also make intrinsic factor. The chief cells, and so we want to think about, okay, the chief is in charge. The chief is the most important. So what is the most important thing that the stomach does? It produces pepsin. So the chief cells produce pepsin, or pepsinogen, sorry. And then again, in the presence of the hydrochloric acid produced by the parietal cell will then be converted to pepsin, and then it becomes a positive feedback mechanism. Okay, now our stomach secretion is under hormonal control. And so this enteroendocrine cell right here is the hormone producing cells within the gastric glands. So there aren't separate glands themselves that are hormonal that affect the digestive process. They're just individual cells, and they're all the enteroendocrine cells. So in this particular case, the enteroendocrine cells produce gastrin, and it's really important that you know gastrin is the hormone that promotes gastric secretion. And we'll talk more about the regulation here in just a little bit. But that is what the enteroendocrine cells of the stomach produce is gastrin, G-A-S-T-R-I-N. Wow, that hurt to figure out how to spell that. Okay, so if we go back to our notes, we've got mucous neck cells producing a little bit of acidic mucus, not the alkaline that we find in the goblet cells of the rest of the stomach, rest of the lining of the stomach. Parietal cells there make hydrochloric acid and intrinsic factor. We talked about intrinsic factor back when we were doing blood and how vitamin B12 is necessary for proper red blood cell production. And your body cannot absorb vitamin B12 if it doesn't make intrinsic factor. So, and we did discuss this back when we were doing blood, and how if a person has gastric bypass, that they're always going to need B12 injections later on in their life, because their stomach won't be making intrinsic factor anymore, so you can't absorb vitamin B12. You can't take it as a pill because it's just going to go right through you and not be absorbed. Okay, and then that vitamin B12 would be absorbed in the small intestine. Okay, so chief cells make pepsinogen, and then enteroendocrine cells make gastrin. We're not going to worry about the other hormones right now because the stomach's just going to make the gastrin, but later on we'll look at other hormones that enteroendocrine cells make. Okay, so just two more things about the stomach. The mucosal barrier, like I mentioned just before, made of bicarbonate-rich mucus, so alkaline mucus made by the goblet cells in the simple columnar epithelium. Okay, the second reason why the stomach can resist that acidic environment, in addition to the mucus, are the tight junctions of the epithelial cells. So it's really important that we don't have a break, that we have a continuous simple columnar epithelial lining within the stomach. The cell membranes of the glandular cells are impermeable to hydrochloric acid, so they're not going to break down. And because it's epithelium, the surface epithelium typically renews itself every 3 to 6 days. So there's constant turnover. So as long as you don't have some other issues along with your stomach, then you should be fine. You shouldn't have to worry about any inflammation or any ulcers or anything like that. Unfortunately, if the mucosal barrier is breached, which we'll talk about in just a second, then you're going to get gastritis. And gastritis is going to lead to, or can lead to gastric ulcers. Gastritis is, in about 90% of the cases, is caused by the presence of the H. pylori bacteria. We were just talking about that. I love when my 16-year-old starts talking about stuff. But so anyway, or maybe it was oh no, it was my anatomy daughter. Sorry, it was the other one that I would expect to talk to about this. But so we were just talking the other day about H. pylori and how most of our ulcers are caused by first an infection with H. pylori, and then gastritis happens, and then we get that inflammation in there, and it breaches that mucosal wall, and then we start to get breaking down of the lining, and we get an ulcer. Um, H. pylori is a nasty little bug. They like to grow in an acidic environment. And I was telling Missy, I said, you know what, when I was in your position, your age, as a, you know, senior in high school, I mean, a senior in college in what, 1980 something, six, I guess I would have been 1986. And I said, we didn't even know H. pylori was a thing because, or at least grow, you know, producing ulcers, because we couldn't grow it in culture. We didn't really know, you know, the acidic requirement that that organism had. And so that's why if you've ever been on H. pylori treatment before, not only do we give you the antibiotic, but we give you a proton pump inhibitor. And so what that's going to do is stop the acid production. And you know, living in a less acidic environment, the organism can't thrive, and then you can get better. So in case you've ever had to encounter that, I guess it's kind of a beast. Missy's dad's had it like 3 times, and my son had it once, and I'm glad I don't have it. All right. So it must not be the food that I fix. They must have got it somewhere else. Okay, one last thing. When we chew up our food and we swallow it, that food becomes a bolus. And so we have the bolus coming down the esophagus and into the stomach. And then the stomach is we're gonna secrete about 3 liters of gastric juice during the day. So it's gonna be quite watery as the material leaves the stomach, and we call this material chyme. That's what goes into the duodenum. And depending on what we're eating, I mean, it's always going to be acidic, but sometimes it's fatty chyme if we're eating, you know, went to McDonald's or something like that. In the stomach, we have protein digestion taking place with pepsin, of course. In children, babies in particular that are, you know, surviving on milk, they'll also produce another hormone called renin, which is not the renin that we have in the kidney for blood pressure control. It's a different renin. And so, and you know, we selectively secrete hormones for a period of time in our lives, you know, like lactose, we're only supposed to produce, I mean, lactase, we're only supposed to produce lactase for, you know, while we nurse. And then once we're weaned, we should never be eating milk and dairy products again. And so, and here's the interesting thing while we're on the topic of digestion. For those of you that are lactose intolerant, guess what? You're the normal. Those of us who are not lactose intolerant that can digest the lactose in milk, the milk sugar, we're the mutants. And it's been an interesting thing that it's been, I think, about 7 or 8 times in the history of the human population that this mutation has come back. So we'll have where we produce lactase all of our lives long, and so it's interesting. Sometime I would like to map that with human history and what we were eating, you know, hunter-gatherers, and then when we started to do agriculture, and then making cheese and ice cream and all those kinds of things. So it'll be interesting to see how that matches up with what we're doing. But yeah, I'm a mutant. Well, I'm a mutant for a lot of reasons, but yeah, I can break down lactose. Okay, here's an important thing. Aspirin and alcohol can also be absorbed in the stomach mucosa and not just in the small intestine. So that's why you get drunk so quickly after drinking copious amounts of alcohol. It's supposed to go to your liver. Remember the hepatic portal vein, which we'll talk more about it with respect to what we're absorbing from our digestive system. Goes to our liver, but zips on by. If we're drinking a lot of alcohol in a short period of time, our liver can't process all of that, and then it's going to go up to your brain and make you drunk. So that's how that works. And then aspirin. We just don't see taking aspirin too much anymore. We've found some harmful things with aspirin intake. If you are a child with chickenpox and you take aspirin, then it gives you this neurological problem called Ray's syndrome that we don't want you to have. So you should never ever take Bayer aspirin during a chickenpox infection. Aspirin, because it gets absorbed in the stomach and it's an acid, can also cause stomach irritation and gastric bleeding. But as a pain reliever, it's faster than any of the others because it gets absorbed through your stomach. So Excedrin, for example, has acetylsalicylic acid in it, which is what aspirin is. And so the commercials on TV, I remember as a kid, it said, hey, you know, take Excedrin, it relieves your headache 20 minutes faster than other pain relievers. Well, yeah, it does, because it can get into your digestive system 20 minutes faster because it gets absorbed by your stomach and not just in your small intestine. So there's that. I always like that. All right, so let's talk about regulation of gastric secretion. We don't want to be secreting gastric juice, so hydrochloric acid and everything, when there's not food there. So there needs to be some things that get it going, get gastric secretion going, and then things that are going to keep it going during the 18 or so hours that we're going to be working on digesting our food from the time that we ingest it. So we've got two ways, just like, you know, how everything works. We've got a nervous control and we have hormonal control. So because parasympathetic is feed or breed response, obviously the vagus nerve is going to be what's going to control digestion. And so and the enteric nerves as well. So your gut brain. So those myenteric and submucosal plexuses that we saw in the layers of the alimentary canal. So what is the vagus nerve going to do? It's going to increase secretion. It's going to promote movement. So peristalsis, segmentation. It's going to open up sphincters, and sympathetic is going to do everything else. So sympathetic is going to shut down secretion. It's going to stop the peristalsis, and it's going to close up all the sphincters. So stuff shouldn't be moving from one area to another while you're in sympathetic stimulation. And it's a good thing because a good thing that we don't stay in sympathetic stimulation very long, because then everything would just kind of sit in our intestine and our stomach and make us feel gross and everything. So primarily things are being moved along. Under hormonal control, we have gastrin, which is going to stimulate hydrochloric acid and the enzyme production, the pepsin production. And then the small intestine hormones are gastrin antagonists. And the reason why we want them to stop gastrin secretion is that we don't want hydrochloric acid in an empty stomach. And so as the food leaves the stomach and goes into the small intestine, then the small intestine will inhibit the action of gastrin, so you don't keep making that hydrochloric acid on an empty stomach. All right, so there are 3 phases of gastric secretion. The first phase is the cephalic phase. So this is with our head. And like I put right there, it's a conditioned reflex, which is something that's learned or trained, just like Pavlov's dog. That's a conditioned reflex. They saw food, they salivated, but Pavlov rang the bell at the same time as he gave them the food. And so after a period of time, then he would ring the bell and the dogs would salivate. And there it is. So that's what we do. As we learn to like food, different kinds of foods, they will trigger that same gastric secretion response. Sure, we'll salivate, but our stomach will also start getting or start producing the gastric juices, getting ready for the food to come. So what kinds of things stimulate that cephalic reflex? The aroma. So, you know, when you walk into grandma's house and she's baking cookies or something, you're like, oh, mom, grandma's cookies. The taste of food, of course, that's why when you go to a restaurant and you look in the menu and they say, can we start you with an appetizer? So what an appetizer is supposed to do is stimulate more gastric secretion, because you're tasting some food to get you to want to eat more. But because I am a little person and I have a little stomach, if I were to eat an appetizer, I'd be full. So I just go ahead and get my regular meal. The side of food, you know how even just seeing a picture of food makes you hungry. You look at the labels of your food, and you know that you want to eat that, but then you look at a great value label and it doesn't even have a picture of the food on it, and we don't even want to buy it, right? We want to buy the Del Monte or the whatever that's got pictures of corn or green beans, or the cereal, right? We want to look at that good bowl of cereal that's, you know, you can't eat any of that food on the picture on the box, because the milk is actually Elmer's glue. So, because milk doesn't film, because it's not thick enough, and so it doesn't come out white, it comes out grayish blue. And so yeah, most photos of food are really doctored up to the point where you could never eat that food. You go to Denny's and there's pictures of food on the menu because the food really isn't that good. So it's trying to get you, ooh, you know, food's really good. Here, look at a picture of it, and you'll want to eat it. And then the thought of food. So the more I think about food, especially yesterday, for those of you that fasted, my poor daughter's just like, Mom, I got to eat. And I'm like, no, it hasn't been long enough. And so she kept thinking about food, which made her even more hungry because she had all that gastric juice in her stomach. All right, so the signals are all going to go to the hypothalamus. They're going to stimulate the vagal nuclei that are there in the medulla, that would then send signals to the stomach glands. Oh, I forgot to tell you this one quick story. So I had a student a long time ago, probably 15 years ago. And when she was a teenager, she worked at a restaurant, kind of like a Denny's restaurant in Florida. And so after the breakfast crowd would leave, then the retirees would come in. And so, you know, 9 o'clock or so, they'd come in, and all they'd want to do is just order a cup of coffee and talk to each other and maybe read the newspaper and stuff. And so she said, when the retirees would come in, that her boss would tell the cooks to start frying bacon, just to fry bacon, because then that smell wafting through the restaurant would stimulate their cephalic reflex. And then, of course, people would start ordering food because they were like, oh, that smells really good. I think I want some food. So yeah, marketers do that all the time. They're always acting on our cephalic phase.
Like the smells that they release at Disneyland on Main Street.
Yeah, absolutely. Absolutely. Okay, then gastric secretion. So once the food reaches the stomach, we need to secrete more, because now we've got a big old pile of food in our stomach. So distension, the proteins being broken down into peptides, the low acidity of the stomach, then peptides, caffeine, and because we're increasing the pH from our food, then we want to, you know, lower that pH even more, and then more hydrochloric acid gets released. So gastric phase is once it's in your stomach. So here we can see we've got long reflexes that are going to affect the brain, but then we have short reflexes that are only going to affect that myenteric or that enteric plex, those two enteric plexuses. So when you're eating, you don't have to send the stimuli out to your brain. It's local. And so whatever the stimulus is inside, so it could be, you know, chemoreceptors, mechanoreceptors, stretch receptors, osmoreceptors, change in osmolarity, whatever, can then just hit the nerve plexus and then send the signal right out to the muscle or gland. So that's why we talk about having a gut brain. Your gut just kind of functions a lot of time independent of our central nervous system, because it just takes too long. We just don't need to involve it. Yeah, okay, so the ghrelin, I don't know what the stimulus for ghrelin is, where that comes in, because I usually don't teach about it. So ghrelin is the thing that makes you want to eat. For those of you that don't know what ghrelin is, that's a hormone that makes you want to eat. And then leptin is the one that makes you stop eating. And so I don't know where that comes from. And we don't really know a lot about ghrelin, because we can't control ghrelin stimulus so that we can stop people from eating, because we think that we get no ghrelin shut off. And that's why people just keep eating and eating and eating and eating. But let me look that up, Bryce, and I will tell you some things on Wednesday, whoops, when we meet again, what I find out about ghrelin. So I'll do ghrelin and leptin and how they are antagonistic to one another. Okay. All right. So here are, this is everything. So this is a good overview or comprehensive look at what's happening with the stimuli are, how do they, where does it act, and then what is the effect on the stomach. So gastric phase, stomach distension, food chemicals. So the rising pH stimulate the chemoreceptors, and then the G cells are the enteroendocrine cells that cause more gastrin release. That's then going to cause more stomach secretory activity. And now we're going to take a look at the intestinal phase. Now, there are two parts to the intestinal phase. So let's look at this one first, at the stimulatory effect, and then we're going to look at the inhibitory effect. Because in the intestinal phase, we need to, which is when where's my pointer? When the food is actually in the duodenum. So we need two things to happen. First, we need to finish up what's going on in the stomach. So the first part of the intestinal phase is going to be the stimulus will be the presence of low pH and partially digested foods in the duodenum will then cause enteric gastrin release. This was gastric, G-cell gastrin release. This is the intestines, the duodenum, releasing gastrin to finish up this secretory activity. But then when enough material has gotten into the duodenum, then we want to inhibit gastric secretion. So distension of the duodenum, presence of fatty acidic hypertonic chyme and irritants in the duodenum, and then again, distension, presence of fatty acidic partially digested food in the duodenum, is going to release a whole batch right here of hormones, which we'll get to in a minute. But when you stretch your duodenum, then you're going to get the enterogastric reflex, sorry. So what do we want to do with this reflex? We want to stop the stomach sending stuff into the duodenum. We don't want any more juice coming in here. And so we get those local reflexes. We can also use the vagus nerve. Okay, so distension would then go up to the vagus nerve, or it would go just to the myenteric plexus. And then it gets our pyloric sphincter to shut. And so once this baby's shut, then we're done and no more material is going to pass into here. Okay, so when we stretch the duodenum, we kick in that enterogastric reflex that's going to shut the pyloric sphincter. But then we're also going to release a whole slew of hormones here, intestinal hormones, which we'll look at in a minute. Okay, so the intestinal phase is both excitatory and inhibitory. During the excitatory phase, food goes into the duodenum, gastrin released. That stimulates the gastric glands to finish up their gastric secretion. So let's go ahead and get done with this. And then as more material passes into the duodenum, then because of this distension of the intestine and even more of the substances from chyme, then we trigger the enterogastric reflex. So what is that reflex? Well, we're inhibiting the vagal nuclei. So if we want to go back here, we can see, oh, yeah, I'm inhibiting the sphincter, inhibiting those local reflexes that then would keep stuff moving. And then we'll actually use some sympathetic stimulation to tighten the pyloric sphincter. Then we get this gastric secretion of these hormones. So these four hormones, secretin, CCK or cholecystokinin, vasoactive inhibitory peptide, and gastrin inhibitory peptide, stop and think what they stood for, all inhibit gastric secretion. So we're going to use these two right here, secretin and CCK, for something else, a step later on in the digestive process, but we're going to kick them out first to stop gastric secretion. So remember, gastrin promotes gastric secretion, but these four hormones, secretin, CCK, VIP, and GIP, inhibit gastric secretion. So they stop inhibiting. They stop gastrin. All right, so here you can take a look at those inhibitory effects once things get into the duodenum. Oops. So we get the duodenal stretch receptors, and we get the chemoreceptors, targeting the enteric neurons, increasing sympathetic nervous system activity to shut the sphincter and decrease parasympathetic activity, because remember, sympathetic shuts down your digestive system. And so we want to get, and that's going to be through those long reflexes. We're going to go up to the medulla. But then the short reflexes, we're going to stop those enteric neurons in the stomach to keep the food, well, to keep the material, because it's not food anymore. That's already went into the duodenum, to keep the stomach from contracting now. And then we get the enterogastones, which are the hormones, so secretin, CCK, GIP. I don't know why they didn't put VIP in there, but anyway. So then we stop the contractile force and rate of stomach emptying. And there's actually several phases of gastric emptying and what stimulates them and what inhibits them too, but we're not going to go into that. Okay. All right. We're going to talk more about these hormones when we get to how do we control the secretion of the enzymes in just a little bit. So we're going to leave the stomach, and now we're going to go into the small intestine, and we want to look specifically at the anatomy of the small intestine because it's adapted for nutrient absorption. So what does it look like? Well, let's go to this picture. What we've done here in the mucosa, so this is just the mucosa. Here's the submucosa. Okay, down here, and we have our little crypts of Lieberkühn. I just like to say that word, these duodenal glands on here. So we're going to take the mucosa and we're going to scrunch it up kind of like the rugae of the stomach, but much smaller. And they're going to be circular folds that line the lumen of the mucosa. So these large circular folds are called plicae circularis. So let's go here. So plicae circularis are the folds. Let me mark that up. Let me find my, and we'll do it in blue. Blue. All right, so what we're going to do is we're going to fold up, just like we took shag carpeting and then we scrunched up the shag carpeting. Okay. All right, so those are the plicae circularis. Then we have on the plicae circularis all these little fingery things right here. And remember I told you that if you look at the mucosa of the small intestine under the microscope, it looks like a brush border, looks like little bristles off of it. Well, here's each one of the bristles. These are villi. So there's a villus. Oh, these are the crypts of Lieberkühn, not the duodenal glands. So each one of these is a villus. So here, this is one villus right here in this picture. And so they're going to be the little, so if it's shag carpeting, then the carpet would be the plicae circularis, and then little shags, or the long shags, the stringy things that come off of the carpet, then would be the villi. Then we have the so we have the villi are going to be covered, I guess, not lined. So all of this tissue here, these are all simple columnar epithelial cells. So if we look in here, all of this tissue here and these cells here, these are all simple columnar epithelial cells. Here are their nuclei down here. So it looks kind of like kiwi fruit. So there are the nuclei, and then here is in the middle where all the blood vessels are. So this would all be the lamina propria of the villus. And then remember that we're going to have these little dots. Let's make it fatter. These dots here. So every one of these dots is going to be a goblet cell. And so there's going to be interspersed throughout the simple columnar epithelium. All right, so and then forgot one more. At the top of the cells themselves, then the cell borders are all folded like that into microvilli. So this border right up in here, this is really, truly that brush border, but when we're looking at it under the microscope, it's the villi that look like little brushy things. And I'm going to try to copy a video that you can see and give it to you tomorrow, I mean on Wednesday, about what that looks like. Okay, so if we go back to our previous slide. Okay, so plicae circularis are the folds of the mucosa. Villi are the little extensions that come off of those folds, and microvilli are the folds of the apical cell membrane in the simple columnar cells. And so their purpose is, of course, to increase surface area for absorption. Okay, the villi then are where absorption is going to occur, so they need to have a capillary bed and a lacteal on the inside. And then their brush border of microvilli, remember we've got the enzymes embedded in the cell membranes, the disaccharides and disaccharidases and the dipeptidases to finish up digestion. But then remember too that there's going to be a whole lot of ion channels in those microvilli in order to absorb all of the food that we're going to absorb. I guess transport channels, not all ion channels, but transport proteins. Okay, we're going to have lots of lymphocytes in the mucosa, because there's a good chance that we're going to ingest something that's bad that might cause an infection. So we want to have T and B lymphocytes in there, and then enteroendocrine cells, which we'll talk more about in a little bit. So if we go back to this picture, we can see here are the blood capillaries, so the red and blue purpley things right here. And so that's where everything but lipids will be absorbed, and then lipid absorption will take place through the lacteal. So there's a single lymph capillary we call a lacteal. All right. This picture just shows the relationship between where the liver would sit up here, the gallbladder, and then where bile is going to come through the bile duct and then into the duodenum. And then the pancreatic duct is going to meet up with that here and then dump also into the duodenum. So here is that C-shaped 10 inches of the small intestine called the duodenum. And then it's going to turn into jejunum. So the stomach used to sit right here. The pyloric sphincter would be just in front of this, or just behind, back this way to the right. Okay, so we're going to come back to that later. This just shows the villi. So lots of folds on folds. And then here are the microvilli. So these are the folds of the cell membrane. So this is all one cell down here at the bottom. And these are just folds. And then this is all the material that we're trying to absorb. All right. Okay, let's probably just look at let's just look at this last slide, and then we should be pretty good, and I'll leave some time for any questions that you might have. So what are the large intestines for? Well, the large intestine is to take the undigested material and to recover any water, nutrients, ions, especially electrolytes that might still have not gotten absorbed. But remember or know that 90% of the water that you consume has already been absorbed by the small intestine. But there's still a lot of water left, because you know what it's like when you don't absorb water and you get diarrhea. It's really, really runny, and you know, especially people with cholera or dysentery or something like that, it just floods out of them. So there's a lot of water still to be reabsorbed and a lot of electrolytes. So sodium and chloride, and we must be able to recover those to maintain our homeostasis. Our large intestine also then forms and stores the feces. So all of our undigested material then will be excreted from our body. So that remaining material, we dehydrate it, we take the water out. It's going to be mixed with our colonic bacteria, and we absolutely have to have colonic bacteria. In fact, there are some people that have some issues with absorption with their colon and stuff like that. where they don't have the colonic bacteria and they can't make colonic or they can't get that colonic bacteria. So we'll give people feces transplants. And so we'll actually take feces that are bearing those organisms and then transplant them into someone whose colon hasn't been working properly. It's why we eat probiotics. So when you're eating yogurt, lactobacillus subtilis and lactobacillus has got a funny name, like, I don't know. Anyway, so lactobacillus acidophilus, that's what it is. And then what was the other thing? Oh, babies. So this is really interesting. When babies are born, they have no colonic bacteria. And so you gotta let them, I mean, how germy are you gonna let your newborn be? Not very germy, but they still have to get that colonic bacteria from their moms. And so it's just pretty ubiquitous, you guys. Bacteria is everywhere. It's like COVID-19. Some of the mucus that's in our digestive tract will go with the feces, and then some of the lining of our digestive system as well. So why do we want microbes in our gut? Because they produce a lot of enzymes capable of digesting enzymes that are indigestible to us, and so they have a commensalistic relationship with us. We don't really need them in that particular case. This one here with cellulose, we can't digest cellulose. When you do PhysioX 8, which we'll talk about tomorrow, yes. So you should have PhysioX 8 done for tomorrow. And we'll talk about the enzymes and stuff and how we don't have cellulose. And so here's the thing. I don't know if any of you have experienced this, but if you suddenly go on a really high fiber diet, you get lots of gas until your body can kind of accommodate that. Your bacteria just go crazy. They're like, woohoo, look at all of this cellulose we get to digest. And anytime the bacteria produce or break down stuff, they always produce gas. And so that's why, methane cow farts and stuff, that you may be a little more gassy after eating a high fiber diet. So there's the intestinal gas. All of our vitamin K, though, comes from our colonic bacteria. And then it just keeps everybody else in track, in check. I can't think of the word. So that we don't get like diarrhea and stuff. Because if you've ever been on an antibiotic that kills off your enteric bacteria or your colonic bacteria, you get diarrhea. Ugh, it's gross until you can rebuild that bacteria again. So it's good to have them in there. They're supposed to be there. E. coli, that's what E. coli means. Oh, I drew on my thing. But it needs to stay in your colon. Oops, sorry about that. Let me see if I can get rid of that. I don't know why that's doing that. Quit messing around. There we go. And then I was going to tell you one more thing. So those of you that are lactose intolerant, the normal people, not us mutants, here's what's happening to you. So when you drink or eat dairy products, then that sugar is going through you and it gets to your colon and it's still lactose. Okay, so here's the deal, you guys. There are so few carbohydrates, like cellulose, that's about the only one, that your bacteria actually get to encounter because we can digest all of our carbohydrates. So when they get this lactose down in your gut, it's like a bacterial kegger, and they just go crazy. And they're like, woohoo, there got sugar in the house, and they start digesting it and everything, and they produce all this gas, and that's why you feel gassy and bloated and crampy and just everything nasty like that, is because your colonic bacteria went crazy with lactose. So, all right, so we're going to stop there with our stuff, and I'll get a little more professional. Look, I just kind of slouching in my chair here. Does anybody have any questions that you want to ask me about our digestive system to this point? You can either unmute yourself or you can unmute yourself. Yeah, that's right. Or you can chat me and okay. Oh, thanks. I like the Northern Lights too. They were always fun to see when I was at home. Never saw them a lot because Calgary's really bright, and then, hi, buddy. Ethan, you got a friend.
Not necessarily a question, but a comment.
Yes.
I messaged you, but I didn't get the code link to log in this morning. It never showed up on Canvas.
Oh,
And
that's
I
because
messaged a whole bunch of people and they gave it to me. But I know a lot of people couldn't get in this morning.
Because I sent the email at like 8:47.
Yeah, I couldn't get
There's
it either.
nothing on Canvas for me.
Yeah, I also couldn't.
Okay. So save the number. I'll send it out again. I'll post it again. But if you check your inbox, it's not in your inbox?
No, there's nothing
Bryce,
there at
wasn't
all. I
there?
had to reach out to a couple other people and
Oh, I apologize. Okay, well, I'll just post it then in an invitation or in a announcement, and then it'll always be there. It'll always be that same personal ID.
that same number. Okay, perfect. Thank you.
Yep. Yeah, and I apologize about that. Zoom, but Zoom's poor Zoom. I mean, yay, Zoom. Have you seen the meme where it said it has the Freddy from Scooby-Doo in the top picture and said, "So who's under this mask that caused COVID-19?" And you rip off the mask in the next shot, and it's Zoom that created COVID-19 so that they can make lots of money.
I was gonna say,
know
they're
they're
making
not
bank right now.
well, but they're not, because there's a lot of people that are using Basic for free. So, and that's why they're gonna keep putting. I probably think those 40-minute limitations is like, no, please buy us. So, anyway, so does yogurt digest more effectively than other dairy products like ice cream for people that? Nope. Probably wouldn't make a difference. Even though you've got the lactobacillus in there, I don't know. Well, I don't know. And probably goat milk is better because it probably doesn't have as much lactose in it. So that's what I think. But I can look at that and see if the bacteria in the yogurt are actually doing the digesting for you. And then can lactose intolerant people eat yogurt better than other dairy products? Yeah, I don't know about that, Joanna. That's a good question. I'll look that up. Yogurt. But I know that goat milk is a little easier for some people to eat, but I don't know what it is about the goat milk that makes it easier to eat.
Is it possibly because it's not processed in whatever processing they're doing? Like, is fresh? I know they say you can't like sell it and stuff, but is unpasteurized stuff better for you?
There's a lot of people that would argue that, oh, you go and pasteurize it and then you ruin it and stuff. I don't know. I think it's probably the actual composition of the goat milk versus regular cow milk that may be different, but I don't know. And there could be a pasteurizing issue as well. I just don't know anybody that drinks stuff right out of the cow. Well,
like people. I grew up on it.
Yeah.
So I'm used to it that way. I mean, I do drink milk from the store now because I don't have a cow, but
right.
If I had a preference, it would be fresh.
My mom, yeah, when she was a girl, always drank it right out of the cow. And so she even likes to drink half and half because it's so much more like out of the cow than what we get in the store.
Yeah, I milked all growing up.
Yeah.
So.
And my grandfather absolutely refused to drink skim milk, her dad. It's like, don't give me that Blue Johnny stuff. That's gross. Yeah. All right. Well, if we have nothing else, I'll give you my personal Zoom ID thing. So it's always that number. And then we'll meet again tomorrow morning at 9 o'clock for lab. So I will upload that packet right now. Make me a little note. Upload packet. And then we'll see you in the morning. Okay, anything else before we go? Okay, fabulous. Well, we'll start.